Okay, we're going to continue our discussion of numeric integration. And as I've mentioned before, there's tables of values. There's various things that you can do to evaluate an integral. What happens in this case is that there's another approximation that you can use, and this one is called Simpson's rule. And Simpson's rule is actually kind of neat because what it does is it uses parabolas, and it kind of inscribes them under curves and approximates by using those areas under those parabolas to find the area under the curve. Oftentimes we have some really complex integrals that are just difficult to work with, and rules like Simpson's rule and one that we've mentioned before, the trapezoidal rule, are useful in calculating numerically an approximation for the integral. So we're going to use the rule, and I'm just going to point out here Simpson's rule and what it looks like. Simpson's rule says you take delta x and you divide it by 3. Well, delta x you've been calculating before, when you did Riemann sums. The trick is here that you have to understand the pattern. So the pattern is something like this: 1, 4, 2, 4, 1, 4, 2, 4, 2, 4, and so forth, until you get to a 2. Okay, let me correct that real quick. Until you get a 2. My computer's acting up here. 2, 4, and then a 1 finally. So it all depends. Those are just the coefficients for your y values, and you plug those in. All right, there's just a pattern. So I'll show you what this looks like once I actually give you an example when we analyze the table of values. So let's take a look here. We have number 3. All right, we're going to go from -1 to 1, and we're going to have x squared plus 9, all right, dx. All right, this is the function we're going to be analyzing. So let's first calculate delta x, and then we'll worry about how Simpson's rule applies. So I'm going to take 1 minus -1. All right, and I'm going to use here 4 steps. So let me write that in. We're going to use 4 steps. Okay, this is going to be helpful in calculating our delta x. That's our n value. So divided by 4. So 1 minus -1 becomes a 2 over 4, which is 1/2. So these are our increments, our delta x increments half. So let's compute a table of values. So again, I'm going to advise you, at this point, you could use a calculator. Just come up with those steps and get your y value outputs, because you're going to be, working with, fractions in this case, or decimals. So that's just my best advice here. All right. And notice we've got that in there. And now what we're going to do is we plug in these x values and get the outputs for the y values there. All right. So what does it look like? Well, the first one here is going to be 10, followed by 9.25, followed by 9, and it's symmetric, so 9.25, and then 10. All right. And it's a quadratic function, so that explains why we end up getting this symmetry here. So what we're going to do here, the first value 10, it gets multiplied by 1, so really don't worry about that. The second value 9.25 will get multiplied by 4, so I'm going to put times 4. The 9 will get multiplied by 2, all right, and the 9.25 will get multiplied by 4. And then the 10 here will get multiplied by 1. So I guess I may as well just write it in there. All right, so that's kind of the pattern there. All right, and we're going to take the delta x 1/2, and we're going to divide it by 3. All right, and then we're going to say, okay, the first y value is 10 plus 4 times 9.25 plus 2 times 9 plus 4 times 9.25 plus let's see, another 10. All right, and we close that out. The 1/2 is going to get multiplied by 1/3. Basically, when you divide by 3, that's what ends up happening. And when I sum all of this here, I take the sum of all of that, what do I get? Well, I'm going to get 112. So basically, I have 1 out of 6 times 112, and I get 112 over 6 as the approximation for the area under my curve using the Simpson's rule approximation. All right, and actually, just to note, this can be reduced. So you actually get, what is that, 56 out of 3. All right, so that really is the correct answer because you do have to reduce. I'm sorry about that. I just thought about it. I said, wait a second, they're both even. All right, so 56 out of 3 is the final answer there. All right, and I think we've got time for one more example here of Simpson's rule. Again, we're using parabolas to approximate this. So let's take a look. This one is going to go from 0 to 2, and let's say it's a quartic function, x to the 4th plus 3 dx. And we're going to say this one again has 4 steps when we're calculating our delta x. Okay, so let's see what it is. We have 2 minus 0. So here's our delta x. 2 minus 0 divided by 4, 2/4, which is 1/2. Okay, all right, so we're going to compute our table of values here for x, increments of 1/2 here. So we're going to say 0, we're going to say half, we're going to say 1, we're going to say 1.5, and we're going to say 2. And these are the y values. All right, so we have here 3. The next value here is going to be 3.0625. Again, you might want to double check on your calculator. Be sure you get as close to accurate as you can. For 1, you get 4. For 1.5, you get 8.0625. And for 2, you're going to get, let's see, 19. All right, so there's not really any kind of symmetry that we're looking for here. All right, but let's figure this out. So the first value is going to get multiplied by 1, the second one by 4, the third one by 2, the fourth one by 4, and the last one by 1 again. And so we take our delta x, 1/2, and we divide it by 3. We multiply it by the sum of 3 plus 4 times this 30625, all right, plus 2 times 4, plus, let's see, 4 times the 80625, plus 19, okay, just like that. And what do we get? We get a 1/2, and let me clean that up, 1/2 times 1/3, and then the sum of all this right there, all right, the sum of all that is 74.5, okay? So we end up with 74.5 over 6. And so I'm just going to basically double everything. So multiply by 2 because that'll get rid of my half for me. Then I end up with 149, not 19, 149 out of 12. And that right there is the reduced fraction for this answer. So a really nice approximation using Simpson's rule to find the area under the curve of this integral here, or evaluate the integral by using Simpson's rule, finding the area under the curve. So again, we're using parabolas in this case to kind of approximate the area under the curve. A really neat technique Simpson's rule is. So as always, I hope this video was helpful, and remember, like and subscribe.